This is A21 June 2010. Question 6. Complete the table 6.1 by inserting appropriate values of mass and charge for the alpha particle, the beta particle and the gamma radiation. So starting off here, we've already got the beta particle being 1/1840 units, and therefore if that's the case, we know that the beta particle's mass is, if we write down, it's got a charge of -1, alpha is 4,2 and gamma is 0,0 the side. So I mean, if that is the case, then atomic units, this has got a mass of 4 atomic units and gamma radiation has got no mass. Charge then, in terms of their charge, I had put down originally +2 because this is the charge at the bottom, but in the mark scheme they've actually given it as a multiple of 1.6 by 10 to the -19, and so it's 2 times, so that alpha is going to be 2 times 1.6 by 10 to the -19, and that actually gives you 3.2 by 10 to the -19 coulombs. So it's in coulombs, so you just need a watch there. Beta particle is -1.6 by 10 to the -19, and again the gamma radiation is not charged. An alpha particle is released into the atmosphere with a typical kinetic energy of 5 MeV, while a beta particle is typically released with a kinetic energy of 0.2 MeV. How do these decay particles lose their kinetic energy after they're released into the atmosphere? Right, the reason is both alpha and beta are both charged, and that means that they ionize atoms of the substance they travel through. And as a result of ionizing, they lose energy or lose kinetic energy as they do this. So they'll give you a mark for energy being used to ionize and the fact that they are ionizing atoms. Part 2. Explain why the alpha particle has a shorter range in air than the beta particle, even though it is released with more kinetic energy. So you're going to say something about the alpha particle being much heavier and therefore it ionizes much more readily, and that will get you 1 mark. And then the second mark is for saying something about there are more interactions per second. And they also have in the mark scheme, or a greater momentum loss per second, per collision actually. And that's the second mark. Part C. The diagram in figure 6.2 represents the decay chain of protactinium 236 to radium 228 in 3 consecutive stages R, S and T. Identify the decay processes R, S and T and explain your reasoning. So I'm going to write down nuclear equations for the decay processes. We'll just scan in a wee bit so you can see that better. The first one there is from protactinium 23691, and it's decaying to give you a new element which I'll just call X, and it's decaying to give you a new element with it still has got an atomic mass number of 236, but it has got an atomic number of 92. So therefore its number here hasn't gone down, so that's a 0, but this one has increased by 1, so this must be a -1. So the decay process R then, the decay process R then is a beta minus decay, and the reason atomic number increased by 1. Right, S then is from here to here, and I'll just write the numbers down below here. You've got 2, 3, 6, 92, and I'm still calling this element X, and it's going to decay to, now its atomic mass number is going down to 232, and its atomic number is going down to 90. So if I just show you the equation now, and I'm going to call it Y, it obviously has lost 4 from the top line, and it has lost 2 from the bottom, so that has to be an alpha particle. So alpha decay, and the reason is because atomic number decreased by 2, mass number decreased by 4. Decreased by 2 and decreased by 4. Last one, and it's a similar kind of decay, and again I'll write it down at the bottom and then show you in a second. I'm still calling my element Y. So we've got 232, 90Y, and then it's going down now this time to 228, and down here it's 88, and it's Z. I'm calling it Z. And again, it has lost, if you look down at the equation now, it has lost 4 from the top line and 2 from the bottom. And again, that must be an alpha decay. And the reason, as above. So there's 1 mark for each of those.